Vera, Vulkan Engine in Rust for animation. This is the first video of what should become a series. This is not a tutorial, but rather a walkthrough of the development of Vera and what it takes to create an engine, concept-wise. This first video will cover what Vera aims to be in the end and the base engine setup I have today. First of all, why Vera? Vulkan. I've spent the last 2 weeks trying to grab Vulkan concepts through tutorials, examples and a lot of reading. I've had experience with OpenGL in the past, but I find Vulkan way more fun to code with, as you have much more control over what you do, which makes it more complex, but enables you to crush rendering performance. I'm using the Rust Crate Volcano, a safe higher level wrapper for Vulkan, which makes it easier in a way. Engine. There are already a slew of engines out there. I'm interested in discovering the possibilities graphics APIs offer by rebuilding an engine from scratch and simply understanding Vulkan itself better. Rust, the language I will be coding in, and the language the engine will be scripted with. Just because I like Rust. Note that development videos aim to be language agnostic. Animation. This is the purpose of this engine, animating to make visualizations, simulations, etc. in 2 dimensions and then maybe 3, something that I can reuse the moment I want to represent anything, including for my future videos instead of paint diagrams and PowerPoint slideshows, as I'm stubborn not to use Unity or Bevy, but willing to make cool things nonetheless. Core features of the engine will therefore include a window to show the output and fast video encoding. When I see awesome YouTubers making awesome visuals for awesome videos, which most likely correlate, I want to be able to do the same while being able to work on the engine when needed, fixing a bug or adding a feature in minutes. Let's dive in. I chose to make Vera a library crate rather than an executable, so it can be used more easily when importing the Vera crate in a Rust project, as it is meant to be scripted in Rust. Import Winit for window management, Volcano for Vulkan, and ARC, a thread-safe pointer from the Rust std, which is used a lot by Volcano. Create a big struct. Add a constructor to it that will set up everything needed by Vulkan ahead of time. This is when the video will go a lot faster, taking a quick look at Vulkan and how I chose to use it. The base for Vulkan is an instance created using a library with a loaded Vulkan implementation. Use this instance to first create window stuff, an event loop to have it respond, and a Vulkan surface linked to the window to draw on it. Choose what Vulkan extensions will be needed. We just need the common Chronos swap chain extension to create a swap chain later. Pick a physical device available on the user's computer, preferably GPUs for best performance, and a queue family that supports graphics, compute, transfer operations, and can draw on our window. From those, get a logical device and a queue to which GPU calls will be sent. Create a swap chain that will hold the different frame buffers, with the images we'll be drawing on. We'll use at least 2 images in order to have one displayed on the screen, while the other is being updated, and later to encode one video frame while another is being updated, and maybe even a third one is being displayed. Create a render pass that will just clear the image in black before we draw on it. Now we'll create buffers. They are chunks of memory containing data used by shaders, which are the programs that run operations on the GPU. Add memory allocators for them. And now the logic specific to this engine. We'll have a vertex buffer containing the position and entity ID of points to place them on an image using a vertex shader following the wanted transformations of the entity they belong to. I call entity any shape, which points must remain somehow related, like a triangle or square. Create a vertex buffer with dummy triangle data. Place it in device local memory, which will make it faster to access by shaders from the device, but slower to access from our application. We can put it in device local memory because we don't need to update it a lot, not at all actually, for the moment. Moving entities' vertices will happen via uniform or storage buffers, so that updating every vertex's position will happen in the vertex shader for performance. Uniform or storage buffers are alike, each can contain arbitrary data, but storage buffers are larger and slower to access. For now, we only have a single triangle, so a uniform buffer, which can contain kilobytes of data, will be enough. We will also place it in device local memory, although we'll update it every frame. This is because we can take advantage of Vulkan asynchronous behavior, which is the default when calling command buffers, which record GPU operations that will be made when the command buffer will be executed. For example, in order to place a buffer in device local memory, we have to execute a command buffer which copies the data from the host visible buffer we have already filled to the device local buffer we can't access from our application, which is on the CPU side. This command buffer is executed asynchronously, so that several can be executing at the same time. And I know the command buffer has finished its operations when a fence is signaled. What that means is that for best performance, we can execute several command buffers simultaneously. However, we must make sure this won't create conflicts between operations. For example, drawing to an image while updating a uniform buffer used for that drawing is a conflict, as we can't predict whether the uniform data will be updated or not when it will be read by the shader. Yet, in our case, I believe buffer copy operations are faster than update operations, even run on compute shaders. So a way to synchronize calls efficiently would be to have, in a first step, a staging uniform buffer that is updated with the first compute command buffer, while the previous image is being drawn to by a second command buffer which uses the device local uniform buffer. And after that, in a second step, a third command buffer to copy the data from the updated staging uniform buffer to the device local uniform buffer that still contained the data of the previous frame, potentially even while swapping the images of the swap chain for display. Once this vertex and uniform buffers setup is ready, build a graphics pipeline for drawing with our vertex and fragment shaders and our render pass. Create a command buffer for drawing, which will use the build graphics pipeline. Other command buffers suggested earlier aren't needed for now, as we won't update the uniform buffer in this video, as I haven't implemented that yet. And that's it for our constructor. Create another function that will run the event loop of the window. Handle basic close and resize events, and then to draw each frame. First, if the window was resized or is in a suboptimal state, which can happen when moving the window to another monitor, for example, recreate the Vulkan objects that need to be updated. This includes the swap chain, images, and frame buffers that need to know the size of their data. Secondly, acquire one of the images of the swap chain, wait until its command buffer from the previous draw call has signaled a fence, then execute it again before presenting the image to the display. And this is our loop. In conclusion to where we are at, calling Vera create will set up Vulkan for our purposes, fill data buffers and create a command buffer to draw a triangle to a window surface. Calling show on a Vera instance will run a loop updating a window with the images of a Vulkan swap chain, each being redrawn to asynchronously, with the triangle defined when constructing the instance. The triangle doesn't move yet. See you next time.